Hi, in this session we will discuss two important extensions of linear regression models. The polynomial regression that allows us to also estimate higher order main effects and interaction effects, and another extension that allows us to reduce the number of estimated coefficients using regularization, which is called the LASSO model. So again, let's look at the original equation of the linear regression model with only main effects. We have learned how to interpret the coefficients, the weights, based on the different types of features that we have at hand. This equation can be extended by polynomial regression if we allow to include also higher order effects, which are just quadratic or cubic or higher order transformations of the original features. For example, look at feature j, then squaring it would allow us to model also quadratic effects of that feature. And including this in a linear regression model would just mean that we kind of add a new feature that is just the squared original feature j and feed this into the linear regression model estimation procedure, and it gives us an own coefficient for only this quadratic or squared feature. And all of these higher order effects that we want to include need to, of course, first of all, be specified beforehand, and they come along with their own coefficient. Also, the same holds for interaction effects, which is just the product of multiple features. And there are, for example, two-way interactions where we just multiply two features. Also, this goes into this equation here by adding it in addition to the original equation. And they're kind of a modifying effect if two features, for example, affect each other themselves. And also this comes along with its own coefficient here. We have here just, for comparison purposes, shown a table that compares a simple linear regression model with another having higher order effects and some interactions. Just to show or illustrate that we can get a better fit if you look at the R-squared measure, for example. So the implications, if we include higher order interaction effects, are the following. So both types of effects that we are including here make the model more flexible, but also less interpretable in the sense that we get much more coefficients, much more weights, and the more we have at hand, the more we have to interpret, and the complex or difficult the interpretation becomes. And also, in case of a linear regression model, both need to be specified manually. So we need to tell the linear regression model, please use the interaction of feature j and feature k or any other type of feature interactions that we want to include. So we need to specify them manually. Also, the degree that we want to estimate, like if we want to estimate a squared effect or cubic effect, needs to be specified manually. In contrast, if we apply machine learning models, they're usually able to learn these kind of complex effects automatically, and we don't have to specify these things manually. So the marginal effect of a feature cannot be interpreted by the single weights anymore if we include or have this extension of the polynomial regression, because we now have multiple coefficients depending on how often this feature occurs within higher order or interaction effect, right? So, and then if we want to interpret the effect of that feature alone towards the target, we need to take into account all of these coefficients. Again, let's look at the bike sharing dataset. On the left-hand side, we have the linear regression model showing the effect of the temperature feature, which is just a straight line. And on the right-hand side, another including an interaction between temperature and the season feature, for example, which is done in that part here in the model. So this shows the kind of interaction between season and temperature, especially between each single category of season and temperature, because season has 4 categories. And since we have here categorical features with 4 levels, we are using this dummy encoding, leading to 3 coefficients because we leave one category out or define this left out category as reference category, which here in that case is the winter category. By this interaction, or including this interaction here, the model gets more flexible than the model on the left-hand side, which was only a straight line, as we can now estimate different slopes depending on the season. Now we have an interaction between temperature and season that allows us to understand how does the effect of temperature change if the season changes, because apparently we have here different effects, like we can see this from different slopes that we see here. So how do we interpret, in case of interaction, the effect of temperature? Here, since we have the winter category selected as the reference category, the interpretation of the coefficient that is estimated for the temperature feature, which is this 160, refers to the marginal effect of the temperature only in the season winter. Meaning that if we look at this line here, which is this linear model for the winter season, it tells us how the temperature affects our target or number of bike rentals. So if temperature increases by 1 in winter, the number of bike rentals increase by 160. So now if we increase the temperature by 1 unit and are now in spring instead of winter, we need to kind of modify the original coefficient that was estimated only for the winter season, because we then have a different slope, as we can see in the graph here. For spring, the slope is a bit flatter, and yeah, we can see here by how much flatter it is by looking at this part here, which is kind of the estimated coefficient of the interaction of the season spring and the temperature. Meaning that instead of having now an increase of 160, like in winter, if the temperature increases by 1 unit, in spring we only have an increase by 110 roundabout, which is kind of summing up these two coefficients here. For summer, we even have a falling trend. Maybe it's also intuitive that in summer, when the temperature is high, usually if the temperature increases even more, cycling a bike maybe gets more and more unattractive. And this is probably what the effect has estimated here. And meaning that, again, compared to winter, so changing from winter to summer, the effect of increasing temperature by 1 unit will lead to a decrease of about 61 bike rentals. Yeah, and last but not least, for the fall season, interpretation is similar. So now we have looked at interactions. Let's look at what happens if we include a quadratic effect. So the interpretation now of the feature temperature is not linear anymore, because now we have two coefficients. The one refers to the original temperature feature, and the second one refers to the squared temperature feature that we will additionally include in our linear regression model, meaning that we will have this part in our linear regression model that is fitted. So if we now combine quadratic effects and interaction effects, this allows us to estimate completely different quadratic functions depending on the season, basically. It's basically the same as in the linear case. Here, however, we even have much more coefficients that were estimated. And this nicely shows you that kind of the more interactions and quadratic effects we are including, the more complex the interpretation becomes, yeah, because we not only have to look at one single coefficients, but need to look at multiple coefficients and sum them up and combine them and so on, which makes interpretation usually a bit more complicated. Since winter is again the reference category, we can only look at the coefficients of the temperature and the squared temperature feature. And if we move from winter to another season like spring, we need to take into account the corresponding interactions of the temperature feature and the season category that we are considering. So another extension that can improve the interpretability, especially if we have a lot of features and a lot of interactions, is the so-called LASSO. Essentially, the difference is that instead of minimizing only the least square estimate as done for a linear regression model, so what we have in this formula here is we are kind of trying to minimize all of these residuals. These are the differences of the data points with respect to the corresponding point on the line. And this is the difference over here, which is squared and usually summed up over all observations and minimized. In a linear regression case, this is the so-called least square estimate. This is in the LASSO extended by adding up penalization term, which has the effect of shrinking some of the feature weights to zero. And pushing feature weights towards zero is equivalent to feature selection, because then it doesn't occur anymore in our linear combination. And LASSO in the end allows to obtain sparser models with fewer features and therefore as also an interpretable model. One thing that needs to be selected by the user is the so-called regularization parameter lambda, and this is usually chosen by cross-validation. So let's look at an example where we had this action between temperature and season and only linear effects. If we fit here a LASSO model and use, for example, a penalization parameter such that we force the model to select only 6 features in total, so 6 of the features have a non-zero coefficient, and the ones that are pushed towards 0 can be deemed as maybe less relevant for the prediction, according to LASSO at least. Here kind of these 2 values and these 2 values were pushed towards 0. In case of categorical features, LASSO shrinks the weights of single categories because it considers each of them as a separate feature, so to say, although in our case these 3 coefficients here belong to one single feature, the season feature. So this basically does not feature selection in the sense that it selects a whole feature out, because this part of the feature is still in the model. For spring, the weight was not pushed towards 0, and therefore we still need the feature season. And if this is unwanted, there's an extension, the group LASSO, where you can tell the LASSO algorithm to treat these 3 coefficients as a group and either push all of them towards 0 or none of them towards 0, which would then kind of be equivalent to selecting that feature completely out so that you can remove it from the data set, so to say.